Hi again, welcome to the next video in the function series. In this video we review the technique of graphing exponential functions. Graphing is critically important for exponential functions because it helps us to obtain a visual image of what is happening in a particular situation. So you need to understand the three transformations involved. All of these transformations apply in the same way to the four basic exponential shapes. There are many reasons why we need to develop graphs of exponential relationships. Perhaps the prime reason is to depict a pattern in a visual rather than in a mathematical way, and therefore we can obtain better insight into a given phenomenon. As they say, a picture is sometimes worth 1,000 words. Many people, as well as politicians, prominent people and activists, often use the description of an exponential increase. All too often they do not mean that, but it sounds good, and the words conjure up a degree of mathematical exactitude. Definitely the wrong use of mathematics. We know that an ordinary exponential graph looks like the one at the right that I have just brought up. It passes through the y-axis at y equals 1, and it climbs rapidly. Actually, there are 4 versions of the basic exponential curve. You need to be comfortable with all 4 of them, and to appreciate the different comment they make about growth and decay situations. The first basic form is for a growth curve, and that's the common one, and it's got the equation y equals e to the x. Such an equation can be used to describe the population of rabbits in a particular area. It can be used to describe the growth in the number of coronavirus cases, and it can also describe compound interest amounts. The second type of curve is a decay curve and has the equation y equals e to the minus x. Such a curve can describe radioactive decay. It can also describe the concentration of medication in the blood over time. Our third type of curve is a decay curve, and it has the equation y equals minus e to the x. So the minus here is in front of the e, not in front of the x. Such a curve can describe the loss of feeling in a limb over time due to nerve damage. It can be the growth rate in cells with increasing concentrations of a drug, or it can be the principal amount left in each stage when paying off a loan. And our fourth basic form for the exponential equations is a growth curve, which has the equation y equals minus e to the minus x. So there's minus in front of the e as well as the x. Such a curve is showing the improvement in oxygen levels in the blood. It might be the absorption of moisture into a cloth or a sponge of some sort, and it can also be the increase in daughter isotopes when a parent isotope is decaying. Having now established the 4 basic forms for exponential equations, we can now look at the effect of transformations on these equations and on their graphs. The first transformation is changing the coefficient in front of the e. The graph I have here shows 3 exponential graphs with different coefficients. Each curve cuts the vertical axis at the value of the coefficient, and that's because e to the 0 is 1, so we're multiplying 1 by the number in front. In addition, the larger the coefficient, then the quicker the curve climbs. In other words, it is steeper, and that is because a number is being multiplied by an increasing value. So you'd expect it to rise quickly. The gradient increases by a multiplier equal to the coefficient at any given x value. The second transformation is where we add a constant to the exponential term. The graph I've got here shows 3 exponential graphs with different constants and so different vertical shifts. In the basic one we have e to the x. With the blue line we have e to the x plus 2, so a vertical shift through the constant of 2. And the green line shows e to the x minus 2, so the curve has come down 2 units. Each curve cuts the vertical axis at the value of the constant or shift above or below y equals 1. So y equals 1 is our base. If we have the blue curve plus 2, we cut it at 3. If we have the green curve, which has minus 2 for the after exponential, then it comes down to 1 minus 2, which is minus 1. The vertical shift alone does not affect the gradient of each curve. It simply slides the curves up or down until they become coincident. The third transformation is where we actually change the index. The graph shows 3 exponential graphs with different multiples with their index. We have the basic form e to the x. We have also e to the 2x, where the index is multiplied by 2. And in the green curve we have y equals e to the x over 2, in which the x value is halved. Each curve cuts the vertical axis at y equals 1. So changing the index doesn't change the intercept. The change in the index only affects the gradient of each curve. The larger the multiplier, then the steeper the curve is going to be. The smaller the multiplier, the shallower the curve. So in summary of these transformations, if we write the equation of a general exponential curve as y equals a plus b e to the cx, then a represents the vertical shift up and down, b represents the factor or vertical dilation constant by which the curve is stretched up and down, and c represents the factor or horizontal dilation constant by which the curve is squeezed in or flattened out. Before we finish, let's have a look at 2 examples in which we take the equation and break it down to look at the implications of the respective transformations. So the first curve we're going to take is y equals 1 plus 3e to the x over 2. And of course we're going to start with the basic curve of y equals e to the x. And to trace a point, we're going to use the points where x is equal to 2. So if we start with y equals e to the x, then at x equals 2, y equals e squared, which is 7.39. So I've marked 7.39 on the basic curve that you can see there. If we now do the transformation of y equals e to the x over 2, then the y value at x over 2 is 2.72. which is simply the square root of 7.39. So that's easy. If we now multiply by the 3, then that multiplies 2.72 by 3, it goes to 8.15. So we've gone right up in terms of the graph. And then if we add 1 to the equation, then that goes from 8.15 to 9.15, so we move straight up a little bit more. In the second example, we're going to start with y equals e to the x and see what happens when we try to draw the graph of y equals minus 1 plus 2e to the 2x. The basic y equals e to the x curve is the lowest one of the ones in the diagram, and we can see that it goes through the points 0, 1 and through 1, 2.72. Now when we apply the transformation of squaring the e term to make it e to the 2x, then we square the 2.72, which gives us 7.4. The next transformation is to multiply the exponential term by 2, which takes it from 7.4 all the way up to the top, where we can see that it's on the curve 2e to the 2x at 14.8. And then we subtract 1 from each value, as according to the equation of minus 1, and we come back to 13.8. So in summary of drawing an exponential curve, we firstly begin by lightly sketching the basic y equals e to the x curve. And then we draw a second curve to adjust the basic curve according to what the index tells us. Then we adjust the new curve for any coefficient that's in front of the exponential curve, again lightly drawing our new curve. And then finally move the curve up or down according to the constant term, which has to be added or subtracted. Make sure you use a pencil or one of those fiction sorts of pens. You will make mistakes, or you will simply want to improve parts of your final version to make it more beautiful. So that is the story of graphing exponentials. It is a relatively straightforward process, but ensure you understand the implications of the transformations. Thanks for watching this video. Hit the like button and subscribe if you haven't already. Also, go and do some exponential function graphs in Test Yourself 1 on my website at drjaysmaths.com. Add a comment below if you have any questions. Good luck. See you in another exponential video.